As graduate students, like most of us are in this room right now, or might have been at some point in your life, if you're being asked to give presentations which are like half an hour long or 1 hour long, that comes easy to us because we are more familiar with it. But what if instead I ask you to give the same presentation in under 3 minutes? That is the tricky part, because how do we put in our years of research all under 180 seconds, at the same time present it in such a way that it is understandable to the audience, yet it also has to be impactful as well as engaging. And that is exactly the magic that we are going to witness today by our talented cohort of 14 engineers who took up this challenge. Good evening and a very warm welcome to the 2024 edition of the Sustainability in Engineering and Design Talks, or the SEDTalks Presentation Skills Training Series, developed by our Trottier Institute of Sustainability in Engineering and Design, our beloved TISET. I'm Fatima Afzal, your MC for the day, and I'm a PhD student under the supervision of Professor Dominic Frigon in Faculty of Engineering and Professor Stan Kubo from School of Human Nutrition. And I've also been through the process 2 years back as a 2023 change makers, and I'll be the MC for the day. Before we start our event, I would like to acknowledge that McGill University is located on land which has long served as a site of meeting and exchange among indigenous people. We acknowledge and thank the diverse people whose presence marks this territory on which peoples of the world now gather. In today's agenda, first I'll be giving you a brief introduction about SEDTalks program, followed by introducing our judging panel sitting right here. At the end, and then we'll move on to our student presentations, where we have 14 students who will be lined up one after another to give their 3-minute presentations which they have prepared. At the end of all the presentations, you would have a chance to vote for your favorite Audience Choice Award presentation, and we'll be having a short break with food and refreshments. After the break, the selection committee would then announce the winners and the Audience Choice Award winner. To give a background on the SEDTalks program, it was created back in 2016 as a brainchild of Professor Jeffrey Bechtolsson, sitting right here in our judging panel today. It started with the goal of highlighting excellent research, sustainability research, taking place across various disciplines within our Faculty of Engineering. And over the years, TISET has been partnering with Dr. Andrew Churchill to develop a series of presentation skills workshops, group feedback sessions, and individual coaching for students who join our program. Andrew is undoubtedly one of the leading experts in presentation series who has over a decade of experience in public speaking and presentation coaching. The workshop feedback sessions are also often assisted by our past year change makers who take the effort, their time to volunteer to come in to help coach the next cohort of students. Since 2016, more than 100 graduate students have been trained under this program, and over 24 change makers have already given their 15-minute TED Talk style presentation in our annual event. And today, at the SEDTalks event, you'll be hearing from 14 graduates from across all our faculties, each of whom have gone through at least 10 hours of training with us and way more than that on their own over the past few months this fall. From among these presenters, the selection committee will choose 3 students as SEDTalks winners on the basis of their presentation, their content, their delivery, and slides. But at the same time, in addition, starting from this year, the committee will also select 3 change makers separately on the basis of the research project progress and the potential to develop a 15-minute presentation from them. And they'll be continuing with our winter training sessions to give their 15-minute presentations in our annual change maker showcase, which will be happening in March. Now, on to introducing our judging committee for today. Today we have a panel of academic and industrial experts who have kindly agreed to join us. We have Professor Jeffrey Bechtolsson, Chair and Associate Professor in Mechanical Engineering at McGill. We have Professor Ali Saifuto Kildani, Assistant Professor in Chemical Engineering at McGill. We have Professor Sydney Omelon, Associate Professor in Materials Engineering. Rana Yakani, PhD, R&D Scientist in 5 and Plus, and also a proud change maker with us in the past. We have Avram Goldman, ING Manager at Pratt & Whitney, Canada, And we also have Michael Johnson, PhD, mechanical engineer in Siemens Energy. A couple of housekeeping notes before we get started. I'll be introducing each of the presenters, after which they will be coming to the stage and giving their 3-minute presentation. You have a view of the timer in the front and also your presentation right here. After all the 14 presentation, we'll go to the break as planned. So if any of you need to step out for a moment, we request you to do so only at the end of presentations, but not in between, so as to not disturb our speakers. So before further ado, let's get started with our event tonight. First, up on stage, we have Tongyue Liang, a PhD student from Mining and Materials Engineering under the supervision of Professor Richard Cromick. And through her, we are going to listen as to how performance coatings can enhance durability.
As we all know that we want things to last on Earth, it's the same that we want them to be durable in the outer space. One major challenge currently in the outer space is that there are a huge amount of lunar dust. These particles are super sharp and they are fast moving, traveling as fast as a bullet from a gun. Now imagine that the transporters are being hit over and over by thousands of the bullets. This will cause severe damage and eventually leads to the failure. Aluminum and titanium alloys are commonly used materials in the space transportation applications due to their lightweight. However, these materials are too soft for long-term durability. Therefore, this comes to a key research question. Can we develop any materials that can combine lightweight properties with greater durability? To tackle this, we are exploring a type of material called high-entropy materials, composed of at least 5 elements, each contributing to 5 to 35% to the composition. We aim to combine lightweight elements with the harder ones with greater wear resistance. Mixing elements with different atomic size will create a very strong and hard atomic structure that can improve the wear resistance. So we then use an atomic deposition process to create these coatings. In this process, the argon ion will bombard the target surface, causing atoms to be ejected from the target surface towards the substrate surface. And over time, we will build a layer-by-layer coating. Here is one example of our high-entropy coatings from this process. We then evaluate the wear resistance of these coatings using wear tests. First, let's consider some traditionally used materials. Aluminum alloys have a wear rate ranging from 40 to 70, while titanium alloys improve this range to 5 to 35. Our high-entropy coatings, however, shows a significant reduction in the wear rate, ranging from 1.5 to 6. This indicates that this type of material has much less material loss compared with the traditionally used materials, and highlighting its great potential to be used in the space transportation applications. And maybe one day, by continuing study, we will have our transporters to operate longer and more effectively in the outer space. Thank you.
Next up on stage, we have Hoda Ahmed, a PhD student under the supervision of Professor Ziqi Cui in Mining and Materials Engineering, and she'll be presenting on leading lithium-ion batteries into a sustainable energy storage future.
Imagine you are driving your electric car on a beautiful road. Feeling great because you are helping the planet. But beneath this green technology lies a hidden problem. It's cobalt in your car's battery. Cobalt is scarce, expensive, and have environmental and ethical issues. Simply put, cobalt, a main component in batteries, is non-sustainable. So, do we have a better option? Absolutely. Manganese-based batteries provide high energy at a lower cost and more sustainable option. So why aren't we using this material? The challenge lies in the particle size. The cathode particle of the manganese-based batteries is too large, which slows down the lithium movement. So what people usually do is that they crush this particle into smaller ones. However, this small particle with non-uniform morphology tend to agglomerate in the electrode film, producing non-uniform particle distribution and non-uniform volume change during charging and discharging. And this will lead to the cracks formation and fast energy loss. So what is the solution? Here where my PhD project comes in. The solution is simple. It is the salt. Yes, like kitchen salt. Instead of mixing the solid precursor for long time and high temperature to synthesize the material, which led to large particle formation, we add the salt to the precursor. Then we heat the precursor and the salt above the melting point of the salt. The molten salt will facilitate the ion diffusion and speeds up the reaction, leading to reducing the reaction time and temperature from 1000 C for 12 hours to 800 C for 1 minute. After cooling down, the salt will solidify surrounding this small particle. So next step, we will apply another heat treatment. So here, we will heat the product of the first step, but this time below the melting point of the salt, in order to improve any incomplete reaction, while the solidified salt prevent any further particle growth. So after washing away the salt in water, we obtain small nanoparticle manganese-based material with uniform distribution in the electrode film and stable energy. So I'm confident that with my project, we will obtain and paving the way for sustainable battery and sustainable future. Thank you.
Next up on stage, we have Sicong Jiang, a PhD student under the supervision of Professor Lee Jun-sun in civil engineering, and he'll be presenting on decreasing congestion pollution, smarter cars for a greener future.
I believe every one of you has suffered from the traffic jams. Some of you may worry about the time we lost, while others may consider the financial cost. However, what makes worse is the pollution. In 2019, in the United States only, the pollution caused by traffic jams is equal to the pollution absorbed by 1 billion trees. Scientists have been putting much effort in solving this. Recently, with the development of communication and autonomous driving, we have much more powerful tools to solve this. Communication can be the key to this problem. Why? Imagine a very common congestion scenario. In traffic flow, we have some vehicles running at low speed, while others at high speed. When they approach each other, it creates a ripple effect. Finally, every vehicle will involve in this congestion. What if they equip with communication technology? They can get to know the position and speed of each other to achieve a cooperative control. However, it's difficult to design a smart communication system to make the decisions of who and when to communicate. We learn something from the nature. Imagine we have some songbirds. They fly cooperatively with an efficient communication method. They adjust their speed and position according to the movements of its neighbors. No one teaches them, but they learn the communication by themselves. We integrate this kind of self-learning communication methods to our vehicles. And we train and let them to learn the policy in a simulated world. Specifically, we consider each vehicle as an intelligent agent. Every moment, it receives and sending communication messages to each other, and then take actions of adjusting their speed or not. We evaluate their actions through 3 metrics: efficiency, energy, and safety. We give each vehicle a score of reward according to their performance. After they receive this reward, their goal is to maximize this reward through adjusting their communication message. This is so-called reinforcement learning. after thousands rounds of trying and updating, finally, they learn an optimized policy to control the speed and also to communicate efficiently with each other. Compared with all human drivers, our communication method can reduce the average congestion time by 70% and even 50% compared with all autonomous vehicles. And compared with all autonomous vehicles, we can also reduce the emissions by 40%, which means if only 30% of United States vehicles can adopt this communication method, we can save millions of trees and bring a greener transportation system. Thank you.
We have on stage next Lakshya Sethi, MN's candidate from Department of Civil Engineering under the supervision of Professor Jingxia Liu and Professor Andrew Boyd. And he'll be talking to us today on how forever chemicals in concrete is a hidden threat.
Hello everyone. I have a question for everyone. What do you see when you look at this image? Do you see fire, smoke, air pollution? Pretty bad, right? But what about that firefighter spraying huge quantities of that firefighting foam? The military uses hundreds of thousands of gallons of this foam each year for its training activities. Unfortunately, that foam is rich in certain compounds known as PFAS, or per- and polyfluoroalkyl substances. I'm pretty sure everyone here in this room has either heard of or is familiar with the term PFAS. These compounds are known as forever chemicals because they do not degrade easily in the environment. And since they are used in a variety of everyday and daily use products, I'm pretty sure everyone here, including myself, have been exposed to some levels of PFAS. Now, what happens when you spray some of that firefighting foam on the concrete pad? Some of these compounds evaporate, some of them get washed away, while a small portion may seep into the concrete. But what happens when you do this every day for not 1, not 2, but say 30 years? After 30 years, we have a lot of these compounds trapped inside the concrete. But what happens next? What happens to these compounds? Do they migrate? Do they stay trapped inside? Do they leach out of this concrete? Or, due to the highly alkaline nature of concrete, do they transform into other compounds? We don't know. As of now, no one knows. But maybe with my experiments, I might solve some of this mystery. I'll show you how. Through my experiments, I'm trying to intentionally contaminate the concrete cores in lab with a mixture of not 1, but 3 different firefighting foams. And this exposure will be through 2 different methods. The first one will be a slow movement of these compounds under the action of gravity. And the second one, I'm repeatedly applying a smaller volume on the surface of concrete. I will take regular samples, and at the end, I will drill into the concrete to get the PFAS adsorbed at certain depths. The results of my experiment will give me crucial information about how these compounds might travel and how they might transform and give rise to new compounds which were absent from the initial mixture. This data will be very important for future researchers and industry partners to develop sustainable remediation and mitigation techniques for these hotspots of PFAS contamination. And eventually, it might help us transition towards a safer and PFAS-free world for our future generations. Thank you.
Next presenter for today is Stephen Walker, a PhD student from Department of Chemical Engineering under the supervision of Professor Sylvian Coulomb and Professor Kopesinski. And he's going to present on how we can use carbon dioxide to make hydrogen fuel more useful.
Hydrogen gas is one of the most promising alternative fuels. However, there's a problem. For long-term storage, every year it loses 16% of its storage volume. The solution is actually to convert hydrogen gas into methane. The reason why? Methane gas storage is 10 times cheaper than hydrogen gas storage. Now, the question is, how do we efficiently turn green hydrogen into methane? Well, that's where my research comes in. This is my reactor, and it looks complicated, but it can be simplified into this schematic, where hydrogen and CO2 react between temperatures of 300 and 400 Celsius to make methane. Using carbon capture, this process is carbon neutral. I measured the CO2 conversion using a mass spectrometer, or MS for short. Now I want to bring your attention to the most important part of my reactor. This paper-like material actually increases the efficiency of CO2 conversion. The reason is it's called a catalyst, and the catalyst I use is called boron nitride nanotubes. These are tubes of interlacing boron and nitrogen atoms. For a scheme, you can think of them as a bunch of Twizzlers, but 1,000 times smaller. Theoretically, these nanotubes are excellent catalysts. However, they've never been tested for this process. So I tested them, and it did not work. It got 10% conversion at best. So I was thinking, maybe I could increase the conversion. Maybe I can take a metal catalyst like nickel and I can anchor it to the surface, kind of like how you would take a Twizzler and put nerds on it. So the reason this works is small metal particles increase the surface area of the catalyst, which therefore increases conversion. Now, to figure out if I can do this, so using an electron microscope, I pipetted nickel acetate onto a nanotube, and I raised the temperature to 400 Celsius. And as you can see, the metal particles started to look a lot like the nerds on the Twizzlers. So I tested it again. And what I found is that the CO2 conversion increased up to 50%. So what I'm hoping is I can use this catalyst one day to convert green hydrogen into methane as a long-term energy storage solution. Thank you.
We have on stage next Sadia Wasim, a PhD student in Department of Civil Engineering under the supervision of Professor Stephanie Lobb. And she's going to tell us how solar-powered nanoparticles can be used to treat water.
Here's some good news. 74% of the world population has access to safe and clean water supplies. This is roughly about like 6 billion people. But wait a minute, what about the remaining 2 billion people? Here's the thing, these 6 billion people live in urban regions where there are well-developed water treatment infrastructure. However, the remaining 2 billion people live in rural regions marked by yellow and orange where there is no such infrastructure. So do we build these water treatment plants in rural region? Well, that would be a very expensive alternative. Here's the thing. A closer look into these regions shows us that they are located near equator, which means they have sunlight all year round. We can use this as an alternate source of energy. Moreover, these regions require small-scale water treatment systems such as these that can use sunlight and provide for a community of 100 people. Therefore, my project deals with using solar-powered nanoparticles to treat water. The superhero nanoparticles of my interest is called the photocatalyst. These are particles that can get activated by sunlight or light energy to produce short-lived chemical species that can kill contaminants in water. These photocatalysts are traditionally used in the industries using expensive, energy-intensive light sources so that these photocatalysts can operate at their full potential. But I want to use sunlight, and they don't really work that well under sunlight. Why? Well, because they do not absorb different regions of the sunlight. So here's the challenge. I have to improve their performance under sunlight. And how did I do that? I used another nanoparticle. This time around, light antenna nanoparticles. These nanoparticles have special property. They have the special ability of concentrating a lot of light energy at their surface. This light energy from different regions of the sunlight can then be moved to the photocatalyst so that it can now perform at full potential. Now, while doing all of this, I had several challenges, such as the fabrication of these light antenna nanoparticles, deciding how will I attach these two nanoparticles together, and deciding what would be the ideal concentration of these light antenna nanoparticles so that the performance of the photocatalyst increases and does not decrease. I can't show you the results for all of that right now, but I would like to show you the degradation performance of these nanoparticles under sunlight using a modeled contaminant. So here's the curve of the photocatalyst alone, and here's the curve of the modified photocatalyst. There is a 60% increase in the performance. This shows two things. A, my 2 years of hard work, and B, that these nanoparticles can now be used under sunlight and cause up to 90% degradation in less than 30 minutes. So with this kind of a superior performance, they can be used in those small-scale water treatment systems in rural regions. And with that, we will now be able to provide safe and clean water to the 8 billion global population. Thank you.
Our next presenter for the day is Aidan Gerkis, an MNs candidate in the Department of Electrical Engineering under the supervision of Professor Xiaju Wang, and he'll be presenting today on weatherproofing power systems to enable a carbon-free future.
How does your electricity get to you? You might think that it comes from a large power plant, like the Trottier Falls Dam, down to Montreal before being distributed to your homes. But that's not quite true. Your power actually comes from that large dam to over 30 neighborhoods all over Montreal. And your power actually comes from multiple large dams, all connected to the same 30 neighborhoods. Now, with the integration of renewable energy, we're starting to see more and more small power plants, like wind and solar farms, scattered across the province. And these small power plants are, of course, connected to the same 30 neighborhoods. Now, let's take a look at this complex power system and assume that it's experiencing an extreme weather event, which damages just one of these transmission lines. Which transmission line do you think would have the largest impact on the system if it were to be damaged? If you're like me, you might think that it's one of these transmission lines. After all, we do get most of our power from these large generating stations. If that was your initial thought, then you might be surprised, just like I was, to learn that it's actually one of these transmission lines whose outage causes the largest blackout. My research focuses on reducing the size and impact of these extreme blackouts. To do this, we can build a model of this complex power system. And using this model, we can assess the response of the system to hundreds of thousands of different blackout scenarios. From these results, I can compute an index for each component. If the value of that index is high, then I can tell you that that component contributes significantly to extreme outages. Well, if the value of that index is low, I can tell you that it contributes negligibly. This simple approach has one glaring problem. It's just really slow. My goal was to speed that process up, which I accomplished by applying the polynomial chaos expansion method. The polynomial chaos expansion method aims to approximate the response of the system using a simple function that looks like this. Computing this function entails determining these orthogonal basis functions and the corresponding coefficients, which I can do using just 100 evaluations of my blackout model from before. Now, if that was a little confusing to you, that's okay, because the important part is this. From these coefficients, I can directly compute the same indices from before, and should, theoretically, be able to tell you which components are the most critical. Now, to make sure that this worked, I went ahead and tested it. I modeled the response of the power system to an extreme windstorm. Initially, the resulting outage affected over 1 million people. By applying my method, I was able to identify just 2 critical transmission lines in the power system. By strengthening these lines, the resulting outage now affected just 130,000 people, all by strengthening just 5% of the components in this transmission system. While current methods exist which could identify the same improvement, it would take them over 21 days to give you that answer. Well, my method can do the same thing in just 1.5 hours, turning a problem that needs a supercomputer to solve into one that can be solved on your laptop. Using this method, power system operators will be able to efficiently identify critical components in power systems, directing infrastructure investments to maximize their impact. They will be able to design power systems to withstand the extreme storms of our future.
Our next presenter for the evening is Ziqi Cui, a PhD candidate in Mining and Materials Engineering under the supervision of Professor Jun Song. And through him, we are going to learn how we can combat hydrogen embrittlement for a sustainable future.
We are driving over a seemingly perfect bridge. No bends, cracks, or visible corrosion. Did you know that bridge might collapse without warning? You may be unaware that there's hidden danger inside the steel structures we depend on every day: hydrogen embrittlement. This process occurs when hydrogen atoms infiltrate steel, making it brittle and prone to sudden fracture under stress, drastically reducing the longevity of steel. Imagine a bridge designed to last a century, not requiring major repairs or even replacement in just a few decades. By causing premature failures, hydrogen embrittlement forces us to use more energy and resources on replacement and rebuilding, which directly impacts sustainability. My research aims to combat this issue by using nitride precipitates, which are tiny particles in steels that can trap those diffusible hydrogen atoms, preventing them from causing damage. However, some nitrides are better suited for trapping hydrogen atoms, while others may let them through. My goal is to identify the most effective nitride precipitates to enhance steel's resistance to hydrogen embrittlement. To achieve this, we use advanced computational techniques. With density functional theory calculations, known as DFT, we examine atomic level interactions between hydrogen atoms and nitrides, allowing us to probe dynamic process at the atomic scale that current experimental facilities cannot achieve. However, given the complexity and the millions of possible nitride structures, we also integrate machine learning to predict the most promising nitride structures. By combining DFT with machine learning, we're able to rapidly identify a few highly effective nitride structures out of millions of possibilities. This greatly accelerates discovery and reduces the need for costly, time-consuming experiments, contributing to sustainability by saving resources. By enhancing steel with these optimized nitride precipitates, we can increase the lifespan of steel structures by decades, making them more durable and reliable in the presence of hydrogen. By tackling hydrogen embrittlement, we are not just strengthening steel. We're building structures to a sustainable future. My research is not just about metals and steels. It's more about making our world safer and more durable for future generations. Together, let's forge a future where our structures and our commitment to sustainability are unbreakable. Thank you.
Next up on stage, we have Aosong Li, a PhD candidate from Mining and Materials Engineering under the supervision of Professor Richard Kromek. And he is going to tell us today about how self-lubricating coatings can be used for longer operation of space machines.
High friction can create unwanted heat, deformation, and wear of mechanical components for space machines. We all know that lubrication is an effective way to reduce friction and extend their lifetime, finally leading to the reduction of the carbon footprint for the space industry. But in space, liquid lubricant like oil will boil off in the vacuum, and extremely low temperature will harden the grease. In that case, solid lubricant is a good choice. MOS2 is a commonly used solid lubricant in space, and we call it lamellar or layered material because it has this kind of atomically thin planes that are very strong, but the actual force between those planes is very weak. That means they can slide over each other really well. When adding it to some frictional components, let's say a bearing system, what happens to the contact region is, as the inner ring rotates, those planes separate the real contact surface and slide over each other with very low friction, so the inner ring can rotate pretty smoothly. What we are going to do is to produce a coating on the contact surface, not an entire MOS2 coating since it is easily worn away, but MOS2 containing copper matrix coating, which mainly consists of very resistant copper, but also has MOS2 inside. In that case, MOS2 can be replenished to the contact region all the time, even if part of the coating is worn away. That's why we also call it self-lubricating coating. The coating is fabricated using cold spray technology, which uses a high-pressure gas to spray the injected copper and MOS2 powders on a substrate, like this. The copper particles shown as gray spheres can bond due to their ductile property, and MS2 shown as black particles will be entrapped in the coating. The most important parameters we need to optimize include the shape and the ratio of the powders, as well as the gas pressure. All those parameters can affect the coating's structure, like MS content in the coating, which will affect the coating's mechanical properties, like hardness, which will finally affect their friction and wear performance. After knowing the relations between those three aspects, based on coat spray theories and experiments, we can design the coating we want. After trying many times, finally we got this coating with enough thickness, 30 to 40 volume percentage of MS2 content, and uniform distribution of MS2. We tested its friction performance and found that its coefficient of friction stays steady after around 40 minutes, and its steady coefficient of friction reduced around a half compared to the pure copper coating. In future, we want to produce some coatings with much lower friction, and hope they can help the spacecraft work for a longer time and more efficiently. Thanks.
We have on stage next Chukwunonso Moneme, a PhD student from Biological and Biomedical Engineering under the supervision of Professor Caroline Wagner. And through him, let's learn how engineering healthcare resiliency can be done through fluid fragmentation models.
Do we all remember the COVID-19 pandemic from a couple of years ago? It touched each of our lives in one way or another, and we're still very much dealing with the effects of it today. It changed society and the world as we know it, and it led to the widespread implementation of public health measures such as masking and social distancing. Now, these measures worked, but as climate change progresses and the population continues to grow, the risk of pandemics posed by respiratory viruses such as COVID-19 continues to change and grow as well. This connects to Taised's fourth theme of adaptation and resilience in the face of climate change. So the question is, how do we mitigate the spread of these viruses so that we can stop the next pandemic before it happens? Well, to do that, we have to look at how these viruses themselves spread. Respiratory viruses, like COVID-19, spread through respiratory fluids that exit our body when we talk, laugh, cough, sneeze, or even breathe. These fluids can exit our body as large droplets that can settle on surfaces and lead to indirect contamination, or as small aerosols that can stay in the air for an extended period of time and travel even further. So, the shape and size of these droplets dictates the route and range of transmission. Therefore, in order to develop accurate virus transmission models, we have to understand the factors that affect the shape and size of these droplets as they leave our body. Looking at the structure of the fluids themselves, respiratory fluids, such as mucus, are composed of proteins called mucins that are suspended in water. In the presence of viruses, these networks can shift and change, which affects the size and shape of the droplets that we produce as they leave our body. This is the phenomenon that I aim to focus on with my research, and here are the first two parts of how I intend to do that. First, I want to use rheology to analyze the different forces that impact the shape and size of these droplets as they are generated within our body and exit. By using suspensions of respiratory fluids, as well as different types of nanoparticles to represent different viruses, I want to look at how these forces change and how the shape and size of these droplets changes looking at specific fluids with specific viruses. Next, I want to use a custom fragmentation chamber that is both temperature and humidity controlled to look at the sprays themselves. Using a high-speed camera, I hope to get images such as these and compare them under different climate contexts. This also allows us to extend the scope of this research to not just be applicable within a Canadian climate context, but globally. Together, this information should help develop more robust virus transition models, which will enable our healthcare system to implement the most effective public health measures when necessary so that we can stop the next pandemic before it starts. Thank you very much.
We have on the stage next Pouria Rahmati, a PhD student in Department of Civil Engineering under the supervision of Professor Susan Gaskin. And through him, let's learn how we can breathe new life into rivers by understanding turbine aeration.
Thank you for your introduction. It's great to have green energy using dams, but did you know that this affects the aquatic life and kills fish? In warm climates, hydro turbines withdraw air from the lower layers of the reservoirs. This decreases the oxygen level in the downstream rivers and changes the water chemistry and affects the aquatic life. In turbines, the locations where we have low pressure due to the high water velocity, air can be self-aspirated. Researchers have shown that aeration of the hydro turbines by self-aspiration is an effective method to increase the oxygen level in the downstream rivers. However, upgrading existing plants with new turbines may not always be cost-effective. Therefore, turbine outlet aeration using deflector is a retrofit option without disruption on operation schedule. Injecting air through the elbow deflector creates air pockets and forming small bubbles. The oxygenation depends on the shape of the bubbles. Therefore, the objective of my project is to understand the air pocket formation, bubble breakup, and the oxygenation. In order to do that, we have built a vertical test rig. And the parameters that I have studied are flow Reynolds number, which represents the water speed, void ratio, which represent the air mass flow rate. Here are the pictures of air injection through the elbow deflector in different water velocity and different air mass flow rate. By comparing the pictures, we can see that by increasing the water speed, the bubble size decreases. And well, by decreasing the bubble size, we expect to have higher oxygen transfer rate. And the results clearly show that by increasing the water speed, we have higher oxygen transfer rate due to the smaller bubbles, which exactly what we expected. And also by increasing the water speed, increasing the air mass flow rate, we have increase in the oxygen transfer rate as well. The other parameter that is important for us is the pressure drop across the deflector. To have self-aspiration using the elbow deflector, we should have negative pressure drop across the deflector. And by looking at the results here, we can see that by increasing the water speed, we have decrease in the pressure drop, and it makes it more negative, which is exactly what we needed to have air self-aspiration. And we hope that the outcome of my research increase the oxygen level downstream rivers, and we hope we never see dead fish because of the low oxygen. Thank you.
Our final presenter for the evening is Farzaneh Abedini, a PhD candidate from Department of Civil Engineering under the supervision of Professor Timshia. Through her, let's learn how we can protect critical infrastructure for sustainable living.
For decades, underground structures showed great resistance against earthquake that made the engineering society to believe that they are naturally safe, like superheroes of infrastructures. Earthquakes? Nah, tunnels got this. But what if they don't? 1995 Kobe earthquake, Japan, and the collapse of the metro system. This can also happen here in Canada. And then imagine the ripple effect. Lots of people will seek for plan B, probably cars, and we will have worse traffic, fuel consumption, and a surge in the carbon emission. And we also need to spend time, money, and massive resources to rebuild everything. This is exactly where my research comes into the picture. With the results of this research, we can find the weak links and fix them in advance. We can modify the design codes, and we can build a more resilient city. Did you know that Canada experiences more than 5,000 earthquakes annually, most of them minor in magnitude? Western Canada is known for its seismic activity, but there is also another area here in Eastern Canada where we have cities like Toronto and Montreal. Seismic activity here is not as intense and not as frequent of Western Canada, but the risk is still unique. Why is that?
because we have a highly populated area here, we have aging infrastructures, and we have a specific soil condition that can amplify the seismic waves. Yet, research on seismic response of tunnels in eastern Canada is lacking. Understanding the seismic risk goes through three elements. First, hazard. How likely is that even earthquake happening here? Second, fragility. How is the probability of the structure to be damaged, and then the consequences? What will be the consequences of that? Fragility itself is a complex part of this research. It's like solving a complex puzzle that we need to understand the effect of different pieces, like depth of the tunnel, the concrete properties, the soil or rock material properties, and the interaction between the structure and soil or rock. To do so, we build a comprehensive framework. First, we collect data based on common scenarios, site-consistent material properties, and earthquake records. We do sampling to get the variability in different parameters like the burial depth of the tunnel and material properties, and we generate thousands of numerical models to build a comprehensive database of the tunnel's response. Then, we use machine learning techniques to quantify the damage and establish the relationship between the damage and different parameters. Then, we calculate the probability of the damage. What will be the probability of damage based on different parameters? Up to now, some cases show that while some tunnels are pretty safe, there are cases that are more vulnerable and need more attention. Then, we conduct an expert-based survey to assess the risk. If my research can find even a small weak links between the kilometers of the metro system, and then we can fix them in advance, then it's totally worth it. Thank you.
With that, we come to the end of all our 14 presentations today, and it was indeed a reminder that sustainability should be thought from an interdisciplinary point of view than a single way of approach. But let's not forget to give a huge round of applause to all the 14 engineers who presented today. They worked really hard and did a good job today. Now, as planned, we are moving on to our break, but don't leave yet. We have food and refreshments for you outside. At the same time, it's time to vote. So Parisa would be having sheets of papers. So please make sure to collect your voting paper ballots from her and also return to her once you're done. And let's reconvene here in this room in half an hour, around 6:15, when judges would be announcing the results.
Well, thanks everyone for being here and for taking part, and thanks also to our judges for doing the very hard job of trying to choose, three winners for tonight and 3 change makers out of these 14 excellent talks. We were just discussing in the discussion and with the selection committee, and saying that the person who gets 4th place in the Olympics, it's not because they did anything wrong, but you might be 1/1000th of a second off of this time. And so for all of you, I want you to take that away, that we were very impressed with all of the talks, and unfortunately we have to pick 3 speakers or 3 winners for each of the 2 categories. When we're looking at the 3-minute thesis, we based it, so the first category is for the winners of tonight's SEDTalks showcase. That's really based entirely on what the delivery of these 3-minute talk was tonight, and that's what we based the selection on. When we talk about the change makers and selecting for the winter program, additional factors come into that. That is, we want to represent the diverse areas of research within the faculty, and so that might be influenced by who has given past SEDTalks in the winter showcase in the past, as well as the depth of research and the level at which students are. So if you're very early in the program, we would encourage you to come back and do this again when you get further along with more results and are able to more fully develop what might now be a proposal into a full 15-minute talk about the work that you get towards the end of your degree. So without further ado, I'll make an announcement of our winners for tonight. So for the 3-minute thesis competition, the 3rd place was a split vote for a tie, with Aidan and Kate taking 3rd place. Congratulations. Our 2nd place winner tonight for the 3-minute thesis competition is Ziqi. And our top 3-minute thesis for tonight is Sadia. So congratulations to the 4 of you for your performance. Now to the change makers. As I said, the selection criteria is a little bit different, and so we have 3 change makers identified. The third place change maker goes to Hoda. Our second place change maker is Stephen. And our first place change maker, also Sadia tonight. So congratulations, Sadia. And showing that the selection committee doesn't know everything, the Audience Choice Award goes to Farzaneh. So congratulations to all of you, and hopefully for all of you that were taking part, you all got something positive out of this experience. We really look forward to this event in the fall and to the winter event with a lot of eagerness, and from my point of view, to see and learn all of the great research that's being done inside of the faculty and in the areas of sustainability. I'd also like to thank, of course, Andrew Churchill for all of the work in coaching through the fall semester. And Fatemeh has taken a real leadership in the Changemakers program, SEDTalks program. So thank you, Fatemeh. And of course, to Irene, to Parissa, and to Monica for all the work in making TIZED run, of which this program is just one of many. So thank you to all. Appreciate your involvement in SEDTalks. Yes, absolutely. So we'll bring it. Okay, perfect. So let's bring down the winners for tonight for a couple of pictures. And thanks to all of you for taking part and for being here in the audience and supporting your colleagues and friends. Thank you.